Okay. Hi, I'm Zev. I work at RightPoint in Boston, and I am going to be talking about juggling and Swift. It doesn't really have anything to do with Swift, but you know, the T-shirt and the whole thing. So I talk with a lot of junior developers and people trying to get into development, and they often ask me, how can I learn to make an app? Because they're maybe going through some tutorials and kind of learning the basics, but wondering how to advance from there to making a full-blown app. And what I usually tell them is go and make a better whatever. Like find some app that already exists that you like and go make a better version of it. You're not going to have an original idea. They're very rare these days. There's like 50 of each kind of app. But go and find an app category that you like and make something that appeals to you. Maybe don't make a better app, but make an app that you want to see. You know, put your spin on it, kind of do it your own way. And that is an approach that I've taken for some apps that I've worked on. And the one I want to talk about right now is an app called iJuggle by a guy named Nathan Peterson. He's a chip designer at Intel, I believe. And he made this app called iJuggle. And at one point it stopped working. And so I started trying to figure out, well, maybe I can make my own and kind of put my own spin on it and do the things that I wanted to do. So what are my qualifications for this? So these are my parents. Both, they would call it eccentric performers. I like to tell people I was raised by clowns. I ran away to join the circuits. And I've been into sort of juggling and mixing juggling with my interest in technology since a young age. Here are some graphics I made when I was 11. And so I thought I would take a crack at learning how to build a juggling app that can simulate juggling just like this other app that I liked. And so this was the first question I faced when trying to do this. How can I learn how to notate a juggling pattern? And this led me down a Wikipedia rabbit hole. I sort of vaguely knew that there was a notation, kind of like music notation or knitting notation, something that lets you write down a few characters and get an idea across without having to spend pages and pages writing things out. I came across these amazing videos by a guy named Colin Wright, who was one of the original developers of juggling notation in the 80s. And I found myself sort of falling down the rabbit hole and getting immersed in this world. So we need to establish some rules to simplify the juggling that we're going to talk about, because there's a whole world of juggling that is like more complex than we want to be talking about, at least at first. We're just going to be talking about the basic. This is called a 3-ball cascade, where every ball visits every hand in the same order all the time. So notice that it's not this, which a lot of you may have been thinking of as sort of basic juggling. This is called a shower. This is actually quite a bit harder than a cascade. We're going to stick with the basic cascade, and we can apply a few rules to this. So our rules are, our hands are going to be fixed. Our hands will not be crossing, moving all around. They will pretty much stay in their lane. The timing is fixed. That means that the hands are always alternating left, right in this even metronomic beat. They never like do two things on the same side at once, and they never go off the beat. And then the last one is the hands alternate. And a byproduct of the hands alternating is that the hands are basically full half the time. You'll see that this is a little bit of a cheat. They're not actually full exactly half the time, but it's pretty close to say, if you watch either one of my hands, you go full, empty, full, empty, full, empty, full, empty, full, empty, that they are kind of sort of full half the time. So we have this notation, and we can start to talk about what's going on. We can draw a diagram. If you imagine someone juggling and moving through space, and maybe a drone overhead is recording, and you draw out the paths of the balls, what you'll see is we imagine time at the bottom of this graph, and maybe we have a red ball that's here. Whoa, red ball. There we go. So we have a red ball, we throw it, we catch it over on the other side, and it stays in the hand for a beat. That's the beat that is held while the other one is doing something. And then maybe we throw a blue ball from the other side because we're alternating. That one goes here and is held. And then let's do the white ball. And, oh, can't draw in white. That doesn't work. Let's do an orange ball. And we'll throw that one from here. And we can keep looping these. The pattern loops around. And we end up with this cool sort of twisty, bouncing back and forth pattern. Fill in the rest of this. And red and orange. And we can juggle this pattern. And so we have red, blue, orange. Okay, so if I switch back, unfortunately, it'll be hard to see the juggling and the diagram at the same time. But red, so we'll have red, blue, orange, red, blue, orange, red, blue, orange. And you can see that this same order happens in each hand. So if you watch my right hand, it's going to go red. Oh, sorry. I think I got the order backwards. But anyway, the balls are sort of staying in their lanes, staying in the same order all the time, whichever hand you watch. They're always going in the same order. And if we look at the diagram that we've drawn, we can start to ask questions about what it's describing about the motion of the balls over time. We can see that the red ball is thrown here, and then it's caught here, and that it spends 2 beats in the air. It spends 2 beats going from one hand to the other. That's the flight time. We don't care about the flight time. In juggling, the most important thing is the throw. If you get the throw right, the catch will take care of itself. So what we really care about is when the next throw is going to happen. And the next throw happens, we have these 2 beats here, and then 1 beat held in the hand for a total of 3 beats. And then if you look at the blue is also doing 3 beats. And then the orange, 2, 1, 2, 3, yeah, 2 here. So each one spends 3 beats from when it is thrown to when it is thrown again. It's no coincidence that this is the number of balls I'm juggling. 3 balls, 3 beats. Each ball visits each hand in sequence, one at a time. So we call this pattern 3. This is the standard pattern for juggling 3 balls. We can ask, what is the standard pattern for juggling 4 balls? So let's take 4 colors we can see. So 4 balls would look like this. And what you notice is that, did I share correctly? Yeah. What you notice is that I'm doing 2 balls in one hand and 2 balls in the other hand at the same time. They're still alternating. We're still going right, left, right, left, right, left, right, left. The hands are still full half the time, and hands are still fixed. They're not moving all over the place. And so we can talk about what this would look like in the notation. So we might have a red ball on one side, and if you think about the way the pattern works, on each side you throw a ball. In the time that that ball's in the air, you catch and throw another ball, and then you catch the original ball. So that one ball spends some time in the air, and then it's caught and held for a bit. While it's in the air, another ball is thrown, caught, and held for a bit, and they will keep leapfrogging over each other like this. And we can see the rules still hold. The hands are still full half the time. You can see the hand is empty here and here and here and here and here and full for the rest. So they're still full half the time. And of course, on the other side, you can do the same thing. It's going to be offset by a beat because the hands need to alternate. These are not happening at the same time. They're alternating right, left, right, left. We need a color we haven't used yet. There we go. And we can again look at the cycle time and the flight time and see that for the red ball, for example, the flight time is 3, but remember, we don't care about the flight time. We care about the cycle time. Cycle time is 4. We are juggling 4 balls. This pattern is called 4. So this is the base pattern for 4 balls. Notice that when we did 4 balls, the balls always stayed on the same sides. And when we did 3 balls, they were always crossing. This is a pattern that extends through all the numbers, that even numbers always stay on the same side and odd numbers always cross. And so we can make a kind of table of the flight times and cycle times. So if we have number of balls and, whoa, we have flight and cycle. So for 3 balls, we had a flight time of 2, a cycle time for 3. For 4 balls, we had a flight time of 3. They spent 3 beats in the air and 1 beat in the hand for a total cycle time of 4. We could go up to 5 balls. What would you expect to see in the flight time and cycle time columns? Well, we're starting to detect a pattern here. The flight time is always 1 less, and the cycle time is always the same as the number of balls. You want to be careful of detecting patterns and then assuming too much that they're true, but in this case, it does happen to work out. We can also go down. We can think about 2 balls. So 2 balls, if the flight time is 1 and the full cycle time is 2, so what is that going to look like? Well, it turns out that for 2 balls just looks like this. Because the flight time is 1, it spends 1 beat in the air, and there's not enough time in that hand for anything to happen in between. And often when you're doing bigger juggling tricks and you throw in one of those throws, it's so short you don't really have time to do anything, so you'll just hold it or maybe show it. And you'll see that later. And then we can also talk about what 1 would be. So for 1 ball, flight time is 0, and the cycle time is 1. So what does it mean for something to have a flight time of 0? That means it can spend 0 time in the air between throws. And in fact, we can do this. And a 1 will look like this. So it is effectively spending 0 time in the air. It's basically just spending all its time in the hands, but still we observe our rule where each hand is full half the time. So that works out. But we can keep extending this diagram. And troublingly, when we talk about 0 balls, well, the cycle time is 0, that's easy. But we need to have a flight time 1 less. Well, that's -1. What is a flight time of -1? That's time travel. That's not supposed to happen. We will come back to this. Let me throw this on another layer, because we'll want to refer to it later. Another interesting thing that we can do is that we can mix and match different throws. So we can, for example, let's say we're going along here with our 4s. So we got 1 there, and we had a blue one here, and then an orange one here. And let's say we're getting bored just throwing the same 4 throws over and over again. We want to shake things up a bit. Maybe we want to have balls switch sides. So what's up next for a throw? Red is up next for a throw. It's the one closest to the bottom. So let's not throw a 4 like we've been doing. Let's throw something else. Let's do something that will let us throw it over to the other side. Now, a normal throw would have landed here and then been held. But if we want to throw it to the other side, we can't have it land at the same point in time. So that's not really what I wanted. We don't want it to land at the same point in time because that would be here, and there's already a ball from the other hand landing there. And the rules don't let you catch 2 at the same time. There are juggling patterns where you do catch or throw multiple balls at the same time. For now, we're just doing this fixed basic pattern to get the rules figured out. So we can't have it land there, so we need to shift it forward or backward in time. We can't shift it backward. All those spots are already spoken for here. But we can go forward. We can throw it a little higher and have it land a little later, say here. And then the next ball to throw is the green. And the green was previously going to follow the pattern and go here, but now the red one is taking up its space. So instead, we have to go across, or we have to find somewhere else for it to land. So let's just take the next free spot, which is this one here. And then that falls back into the pattern. And in fact, we can now continue the pattern as though nothing had happened. If fall right back into our pattern of throwing 4s alternating on either side. So what has happened here? What have we done? We now have a red ball that is going from here and being thrown again here. So that's 1, 2, 3, 4, 5 beats. And we have the green ball over here that is going 3 beats. So really what we've done is, in the midst of throwing 4s, we've thrown the red ball as a 5 throw. So a throw as though we were juggling 5 balls. And then the green ball as though we were juggling 3. And then we go right back into juggling 4s off into infinity on both sides. We've invented a juggling trick. We've predicted it using this diagram. Now let's see if it works. So remember, this will be, let's see, it was red, green, blue, orange were the ones I used in the diagram, and red and then green switch. So it will be red from my right hand crossing high, out from under the light, and green from my left hand crossing low in 3, 2, 1, 5, 3. We'll do it from the other side. In this case, it will be red from the left hand crossing high and green from the right hand crossing low in 3, 2, 1, 5, 3. And this behavior where the balls are switching which sites in the pattern they belong in is where the notation gets its name, site swap. That's what this notation is called. So let's see if we can simplify. This diagramming stuff is useful, but it's pretty tedious to have to trace out every ball, the positions, keeping the hands the same. Maybe we can simplify it a little bit. We already know that the hands are alternating, so we don't really have to express in the notation which hand each thing is thrown into, because we already know they're going to alternate. The notation and the rules already take care of that for us. So we can simplify that by squishing down the 2 hand sort of tracks, left and right, just squish them down into one. What we really care about was that thing where we needed to know where we could throw a ball in the future, where there was already a free spot or whether a spot was taken up by a ball that was going to be landing there. And so we can try to do that. So let's take our 3 balls again that we had at the beginning. Should be able to do all the same color and it should be fine. So we have our 3 balls. What we can do is we can write this. Let's just say 3 X's. Those are our 3 balls, and they're already spoken for. We already know that those 3 balls are being thrown, and that's happening. And now off into the future, we have all of these potential landing sites that are empty right now. And so we can express those infinite future landing sites as a bunch of spaces. Now, let's say we want to find the next thing to do for this ball right here. All we need to do is find a future landing site, and it could go here, or it could go here, or it could go here, and that corresponds to this X here popping over to this spot, or this spot, or this spot. So we just need to pick one. So let's just say we're going to continue our same pattern for now. So we're just going to go to the next available spot. So that's equivalent to this one jumping over to the next available spot. And so we chop it off the front, we move it over to the end, and we're still at our 3 X's with infinite spaces after them. And we can do it again, and we have 3 X's with infinite spaces after them. But what if we want to throw a different throw? What if our next throw wants to be a 4, say? So on our diagram, that would be this one doing a 4. And it's now taking up a space here while leaving a space open before it. Well, that would be the equivalent of this X going over to here. Say that's a 4, and the rest of these were 3s. And now we have X, X, open space, X. So this simplified notation is still telling us what we want to know, which is where are the possible places that we could throw the next ball. We'll just stop writing the spaces off the end, but let's just assume that they go off into the future. We don't know what's going to happen then. So let's now take this idea of notating possible throws, or rather throws that are already spoken for as x's, and leaving an empty space where we know that a throw could go. And let's see what we can do with it. We're all programmers here. Let's build a finite state diagram. So let's see if I have a page set up for that. I do not, so I will make a new layer. There we go. OK. So we started out with our 3 balls. And as long as we threw 3 throws, those were those nice normal sort of lowish crossing throws, we stay at this state. Now let's throw a 4 like we did just a minute ago. So we throw a 4 throw. Remember, it's staying on the same side. The other ones are crossing. It doesn't matter. This notation takes care of it. All it cares about is which spaces in the future are empty. So we're going to take that first x, move it over 1, 2, 3, 4 spaces. So that's going to end us up in this state here. And let's see, we could, let's say we want to figure out now what to do with this next throw. We can't throw a 1 because that would move it over 1 space, and there's already a ball spoken for in that space. But we can move it over 2 to fill up that gap there. So we will throw a 2, and that would bring us back into XXX. So we can just draw an arrow back to an existing node on the diagram and say that was a 2 throw. And so what have we done there? We've discovered a juggling pattern. This juggling pattern is 4, 2. So we're juggling, and then we're going to throw a 4 on one side, or we're going to throw a 4, and then we're going to throw a 2. And because the hands always alternate, it's going to be a 4 on one side and a 2 on the other. Recall that a 4 is a same side throw that's sort of medium height, and a 2 was that little pop, or really just holding it, because we don't have time to. Anyway, I will throw a 4 on my right, and then a 2 on the left, and it will look like this: 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. All of these are 4, 2. That's something else. Cool. We discovered a juggling trick. On paper. Pretty neat. Let's see what else we can find. So we threw that 4. Now, instead of going right back home, let's venture out into the world a little more. Let's throw another 4. We have room for it, right? We can go over here. So let's do it. Let's throw another 4. Whoops. So that will be a 4. That will take that x from the beginning, run it around to the end. So we will have x underscore x. OK. So we've thrown a 4, we've thrown a 4, and now I see a convenient place to close this up back to the original state. We can just take that x at the front, move it over 1 space, end up again back where we started by throwing a 1. And so now we've discovered 4, 4, 1 as a trick that could possibly work. Well, will it work? Let's try it out. So I'll be juggling, and I'm going to throw a 4 on one side, which is that vertical same side throw, and then a 4 on the other side, again, vertical same side throw, and then a 1. Remember, 1 is that zip across. So it will be 4, 4, 1. Let's try it out. And 4, 4, 1. 4, 4, 1 on the other side this time. 4, 4, 1, and I can run it continuously. 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1. It turns out that any closed loop on this diagram is a juggleable pattern. And furthermore, anything that starts and ends here at what's called the ground state is a ground state pattern, meaning I can just keep looping back from the ground state. I can be juggling 3 and then jump into that pattern and jump back out without having to do anything special. Now let's look at a different type of pattern. This is a classic juggling pattern. I mentioned it before. This is going to be the shower. This is what a lot of people think of as juggling, just I think because it's easier to think about visually, where you're going around in a circle like this. So this is where we start to see where this notation becomes useful, as useful as anything juggling related could be said to be. So let's say I'm a juggler and I'm working on a routine and I'm going to be doing this, and maybe I've set it to music, so I have certain time requirements. And a little bit later, I want to be doing this, the shower. So the normal transition that most jugglers did for probably hundreds of years, or at least about 100 years, would be, okay, I want to start throwing high with my right hand. Cool, I'm going to do that. Did you see that awkward pause? Let's do it again. Pause. Pause. It's not great. If you're trying to keep a flow of a routine going, that's like maybe you want to pause there, maybe not. It'd be nice to have control over that. Let's look at the notation and see if we can figure out why that pause happened and then how to fix it. So I was hanging out here in ground state, and I wanted to start doing a high crossing throw and then a very low crossing throw. It turns out that first crossing throw is a 5 throw. It's the same height as if I were juggling 5 balls. And so we can see what that would look like. I can throw a 5, and that's going to take that first x and go over the 2 x's over 2 blank spaces, and we'll end up at x, x, space, space, x. Make that a little neater. And then the next thing I wanted to do was that 1, that zip across. But look, I can't. There's already an x there. I have to do something else. I physically cannot throw a 1 because there's already a ball in that hand. It will collide. So the next best thing I can do is a 2. So I guess we'll do that. And that will take that first x and jump it over the second x, and we'll get x, x underscore x. Oh, wait a second. X, x underscore x is already on this diagram. Cool. So let's undo that and just draw a line straight to there. 2. And then the pattern I was originally trying to do, so let's take another crack at it. Let's try our 5 again. 5, that will take this x here and jump it 5 spaces to the right, so that's x underscore x, x. And then, oh cool, now I can do my 1. So now I can take that first x and slide it over 1 space. That will put me in x, x, space, x, which again is already on the diagram, so I'll draw an arrow back to there. So now I've found my pattern, 5-1. That's what I was looking for. 5-1 is that shower, that high throw on one side, low throw on the other side. But I had to take 2 steps to get there. I had to go all the way over here on a 5, then here on a 2, and then finally find my 5-1. And that's what jugglers did for decades. Until in the 80s, they started figuring out this notation and realized, oh, cool, there's a faster way to get there. I can go from here with a 4 right into 5-1. I think the reason that this maybe didn't occur to people is that because the throws alternate, that 4 has to be on the opposite side of the 5. So it's really unintuitive if you want to do high throws on the right hand to start with a high throw on the left hand. But in fact, we try it out. So I will be doing my 5-1 on the right hand. That's going this direction. But it's going to start with a medium height, same side throw on this side. And it will happen now. Do it again. No more awkward pause. We go from here smoothly into here with no gap. And that's something that was discovered basically on paper before it was discovered like by jugglers trying things out. Oh, also the 4-4-1 that I showed you earlier, this one is another one that was discovered on paper and then sort of made the rounds at juggling conventions, people telling each other about it because it was discovered with the notation. So this brings us back to, what was that thing about a negative flight time? What's going on there? Let's see. Oh, cool. I drew that on the wrong layer and messed up my template. I will fix that later. So we were talking about this number of balls, flight time, and cycle time. And we can try and figure out what that what that zero number of balls throw looks like by working our way down. So let's start with a pattern that we know. So we had our 4, 4, 4, 4, 4. So that's just fours. Those are the same side throws, 4 balls. Oh, by the way, the average of a sequence of numbers that makes up a juggling pattern is the number of balls. So when we threw our 5, 3, the average of 5 and 3 is 4, and that's how you can tell that that's a 4-ball pattern. There's a proof, but I don't know it. Okay, let's put a couple extra 4s on here. So we already looked at 5, 3. 5, 3 was the one where we were juggling 4 balls, and then 1 crossed high and 1 crossed low. And then we kept doing 4 balls. It turns out we can extend this pattern. We can do 2 5s. And if you do out all the diagrams and everything, you find that you get a 2 there. So what does this look like? We're doing 4s. Then we throw 5, 5. So that's 2 high crossing throws. And then a 2. Remember, the 2 was the little pop, or in this case, I'll just show it. And so this is going to be high crossing throw, show a ball. And that's going to happen. Let's see, this will be blue and red, blue first. So high, high, show. High, high, show. Cool, so that works. Do you see a pattern emerging on the table here? What would be next if we kept extending this pattern down? Well, it looks like we add a 5 each time. And then it looks like this is going down, so 3, 2, so 1 would be next. So what's that? 5, 5, 5, 1. Okay, so that should be high crossing throw, high crossing throw, high crossing throw. And the 1 is that zip across. So I think we will go blue, red, green will be the high throws, and then the yellow will zip across in 3, 2, 1. I'll do it one more time. I don't know which colors I'll do. So that's 5, 5, 5, 1. Let's follow the pattern one more time. Whoa, I don't know what I just shared. There we go. Okay, we're back to the screen. So we have our 4, we have 5, 5, 5, 5, 3, 2, 1, 0. So that's 4 high crossing throws. I only have 4 balls. I don't have any balls left. But I need a ball to have a -1 flight time. That's okay if we can spontaneously produce an anti-ball that will travel 1 beat back in time. Everything should work out. What is that going to look like? So we're going to have our 5, 5, 5, 5. Those all go forward in time. And then if we're going to keep going in our regular 4 pattern that we were doing before, these all connect up in the way that we've been seeing. And that means that we've got a gap here. And we know we need something that is spending -1 beat going back in time. And that's OK as long as an anti-ball is produced, goes forward in time. Everything should work out. We can, in fact, check this by going, let's take a snapshot in time before the event. And we have 1, 2, 3, 4 balls. And a snapshot in time after the event. That's a bad and we have 1, 2, 3, 4 balls. And right in the middle, we have 1, 2, 3, 4, 5, minus 1 for the anti-ball. Everything works out. How does this work in practice? We need to do 4 high crossing throws. And if you listen very closely, I don't know how well the mic will pick up, but you will hear the miniature thunderclap of a ball anti-ball annihilation. So if I can do it. The ceiling's a bit low. Ooh. And no. Again, no. I'll try one more and then put myself out of my misery. Close enough. So we found an interesting trick where the math actually does work out, and it has a lot in common with particle physics in the sense that we can have an anti-ball that moves back in time. I think that is a good place to be done with the notation and open it up for questions.
I think we need to invest in a slow-mo camera for the Boston office.
Yes. Oh, right. Actually,
yeah.
Thank you for, so yes, a slow-mo camera is very interesting for juggling. And it reminds me of the whole point of the talk in the first place, which was that this is the stuff that I had to learn to create an app that does this. Because I thought it would be interesting to have an app where you can type in the numbers and see what the juggling looks like. And so this is the work in progress app. Unfortunately, his head is getting cut off a little bit right now. I will fix that before I ship. This app is in beta right now. But I have this slider down here at the bottom, and I can speed it up or slow it down. And so there's your slow-mo camera. Also, I don't know how well the juggling came across the Teams meeting. So maybe if you catch the recording later, it will look a bit smoother. And here, let me make these multicolor so you can see a little better what's going on. So as I type in different patterns here, we can see some of the stuff we've been talking about. So that's 4. And now what if we did those 4s and then a 5, 3, and a few more 4s? We can see that high crossing, low crossing. If I make it just 5, 3, we'll do continuous high crossing from his right hand, our left, and low crossing from the other side. We can do the 5, 5, 2, 2 highs, and then just a held ball. Oh, cool, the balls are slightly not staying attached to the hands. That's another bug I'll have to fix before it ships. 5, 5, 5, 1. There's the 3 high crosses and the hand across. High, 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 hand across. And of course, 4 5s and a 0. How many balls does it go to? Great question. So remember how I said that the average of the number in the pattern is the number of balls? So we can type in 9, obviously. That's what it would look like juggling 9 balls. Really speed it up or really slow it down. What comes after 9? Well, again, we're all programmers. After 9 is A. And so that's A balls, which is really 10. That's 5 in each hand. Remember, even numbers don't cross. And then we can go up to B. This is easier with the keyboard. So that's B, C. And once you can get into letters, you start thinking about, well, what words are juggleable? So I happen to know that the word app is juggleable. So that's what that looks like. And I ran it through the dictionary. So first of all, Z is the highest letter. So that's what, 36 balls, something like that, 35, 36. Oh, I guess they're crossing. So it would be 35, it'd be an odd number. But I ran it through the dictionary on my computer and found all the words that are juggleable. And the highest word that is juggleable is zoolith. And that looks like that. And if I speed it up, I don't think this is going to work over Teams because there's no motion blur. But OK, yeah, it just looks like a huge jumble of balls. When you see it at full frame rate. So if you look at the recording later, they kind of blur together and you see these like different height arcs and it looks kind of cool. But that's actually a lot of using notation to find higher juggling patterns with bigger numbers is finding ones that look nice. So for example, there's a pattern I like called 5-3-1, where we have the 5 is a high crossing throw, the 3 is a medium crossing throw, and the 1 is a low crossing throw. And that gives us this high, medium, low stacking. And they all kind of peak at about the same time. And the cool thing about 5-3-1 is you can just keep adding successive odd integers to the beginning. So here's 7-5-3-1, which is a 4-ball pattern. And here's 9-7-5-3-1, which is a 5-ball pattern. And now you can really start to see this pattern emerge, that they all go up to different heights and peak at the same time at different heights, and then all come down again, and go up and peak, and then come down again. And so some of these look really pleasing. Another one of these is if we reverse it and we do 1, 2, 3, 4, 5, 6, 7, 8, 9. That is a, what is that? A 5-ball pattern where they all come down on one side and then go up on the other side and then come down and go up on the other side and keep alternating back and forth. So there's some really pleasing kind of visual aspects to this. And this is where juggling kind of overlaps with dance and other types of movement, where you're not just worried about the numbers and showing off how many balls you can juggle. You're really looking for pretty shapes and trying to figure out what looks good together.
This is fantastic.
So if somebody wants to see DB 97531. Cool. So yeah, those are alternating successive decreasing odd integers. And we can just keep going up. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Whoops, what did I do? J, K, L, M, N, O, P, Q, R, S, T, U, V. This is surprisingly hard. W, X, Y, Z. So that's the highest count version of the decreasing. Of course, that's only if you set your maximum to Z. And you could just keep going up. It just gets harder to type. And I thought, well, people can't juggle above around 13 or 14 balls at the very peak of like juggling performance. So at this point, it's more a mathematical curiosity. But the numbers totally work. You could go up as high as you want if you have a notation for entering those numbers. And you can really see that they all go up and peak, and then all come down, and all peak and come down. So there's some definitely some pleasing patterns here. Any other questions? Cool. Thanks for watching.